limits at infinity and horizontal asymptotes. You might remember back in sections 2.2 and 2.4, back from page 80, we learned that a vertical asymptote was possibly where you set your denominator equal to 0. In Precalc, we had learned that if you reduced your rational function down to its lowest terms, and then you set your denominator equal to 0, that typically gave you a vertical asymptote. But in calculus, we got a more formal definition of a vertical asymptote, and that was that if you took the limit as x approached a particular value for a function and you got either infinity or negative infinity as your answer, then x equals that value you were approaching was a vertical asymptote. And so we would set the denominator equal to 0 to get possible vertical asymptotes, and then we would test them by the definition of a vertical asymptote to make sure that when we took the limit approaching that value, that our limit did go to infinity or negative infinity from either the left or the right. An example of that would be like if I have x squared minus 4 over x minus 2. That doesn't have a vertical asymptote at x is equal to 2. Because if I go through and I reduce this rational function, this is a difference of squares x plus 2x minus 2, the x minus 2's would cancel out, and that would just leave me with x plus 2. So this literally graphs like a linear function, y equals x plus 2. It just has a hole in it in the graph at positive 2, but it does not have a vertical asymptote there. So if I had missed reducing that down and I had thought there was a vertical asymptote at x equals 2, if I tested it by taking the limit as x approaches 2 from either the left or from the right, I would see that it didn't go to infinity or negative infinity. So now I want to look at the idea of horizontal asymptotes. And over on page 250, they tell me that if I have a function defined on an interval from a to infinity, if the limit as x approaches infinity of that function is equal to an actual numerical value L, then y equals L will be a horizontal asymptote. So if the limit as x approaches infinity or negative infinity of a function reaches an actual limit, then that limit will be my horizontal asymptote. And so we also had a practical way of finding horizontal asymptotes in Precalc, and that was by comparing the degree of the numerator and the denominator when I had rational functions. So if the degree of the numerator was larger than the degree of the denominator, I didn't have a horizontal asymptote. If the degree of the numerator was less than the degree of the denominator, then my horizontal asymptote would be y equals 0. And if the degree of the numerator equaled the degree of the denominator, then my horizontal asymptote would be the leading coefficient of the numerator over the leading coefficient of the denominator. So again, I have the practical way that we had in Precalc, but in terms of proving it or justifying it, then I would want to do the definition that they give us here in calculus on page 250. So for example number 1, says, find the infinite limits, the limits at infinity, and the asymptotes for the function whose graph is shown in figure 5. All right, when we're talking about infinite limits, we're talking about limits that go to infinity. So when I'm looking at my graph over here, I can see this goes off to positive infinity at negative 1. This goes off to positive infinity at positive 2. This goes off to negative infinity at positive 2. So all of those would be infinite limits. And I could write those by saying the limit as x approaches negative 1 from the left-hand side is positive infinity. The limit as x approaches negative 1 from the right-hand side is positive infinity. The limit as x approaches positive 2 from the left-hand side is negative infinity. The limit as x approaches positive 2 from the right-hand side is positive infinity. When we're talking about a limit at infinity, that's when you take the limit as x approaches infinity. So I'm saying as x goes off to a positive infinity or as x goes off to a negative infinity, what is my function doing? Well, as x goes off to a positive infinity, you can see my function's going to go like this. You can see that it's going merrily along and then all of a sudden it turns and it just levels off right there. And we know that when we see a function level off like that, that typically indicates there's a horizontal asymptote there. So that makes sense then that when we're getting that limit at infinity of 4, that might indicate that there's a horizontal asymptote there. All right. Similarly, if I take the limit as x approaches a negative infinity, I'm looking at what's my function doing as I go to negative infinity. So I can come over here and trace it, and it's going merrily along, and then all of a sudden it levels out again, and it appears to be approaching one singular value of a positive 2. So based on the definitions that we have for vertical and horizontal asymptotes, we could say that we have vertical asymptotes at -1 and +2, because if you take the limit as you approach -1 from either the left or the right, I didn't even have to have both, and I got an answer of either infinity or negative infinity, then that would cause a vertical asymptote. And similarly here, because I approached 2 from either the left or the right and got either negative infinity or positive infinity, I wouldn't even have to have both as my justification. That would give me a vertical asymptote at 2. Then the definition that we picked up today, if I take the limit as x approaches infinity or negative infinity and I get a limit, then that value would be a horizontal asymptote. And so I have a horizontal asymptote at y equals 2 and at y is equal to 4. All right, so look at example number 2. Example number 2 says find the limit as x approaches infinity of 1 over x. All right, so if I'm able to find a value here, of course a limit at infinity is going to create a horizontal asymptote. So let's see if we have a limit. If I'm looking for the limit as x approaches infinity, we're basically saying we're going to plug in values for x that just get larger and larger and larger without bound. So a good way to test that is to plug in like 1, 10, 100, 1,000, 10,000, million, billion, trillion, whatever you need to do. So when I plug 1 into this thing, I'm going to get 1. If I plug 10 into this thing, I'm going to get 1/10, so 0.1. Plug in 100, 1/100th, 0.01. Plug in 1,000, 1/1,000th, 0.001. And so we begin to see a pattern. We've talked about this before, that when my numerator stays the same and my denominator gets bigger and bigger and bigger, the overall fraction is going to get smaller and smaller and smaller. It's not going to go negative because I have a positive divided by a positive. So it's just going to get smaller and smaller and smaller and go to 0. Similarly over here, if I did the same thing with negative values, I would have 1 divided by -1 is -1. 1 divided by -10 is -1/10, so -0.1, -0.01, -0.001, -0.001. So in that case, numerator staying the same, denominator getting larger and larger and larger without bounds, so overall fraction getting smaller and smaller and smaller. It's just that it would be a positive divided by a negative. And so each of those values would again be getting closer and closer to 0. And sure enough, if I graph y equals 1 over x and I look at that graph, as x goes off to positive infinity or as x goes off to negative infinity, absolutely I am seeing horizontal asymptotes there at 0. So the graph backs up what we just found algebraically. Now we should be able to do limits like that without a calculator, with just that logic of numerator staying the same, denominator getting larger and larger, overall fraction getting smaller and smaller and going to 0. Over on page 253, they give me a property that kind of follows suit with what we were just saying. It says if r is greater than 0 is a rational number, and you have the limit as x approaches infinity of 1 over x to the r, that's going to be equal to 0. Or if you have the limit approaching negative infinity of 1 over x to the r, again, r is greater than 0 and is a rational number, then you're going to get 0. It's that same idea of the numerator is staying the same, the denominator is getting larger and larger and larger, so the overall fraction will get smaller and smaller and smaller. And whether it's a positive divided by positive or a positive divided by negative, still going to 0. I would expand on that a little bit to say it doesn't just have to be 1 in the numerator. And here's my logic for that. If you have a constant that's being multiplied by something, so I could rewrite a number over x to the r as that number times 1 over x to the r, where that number could just be any constant. We have a property that's a constant multiple property that says you can pull the constant out in front and then take your limit. So this limit is still going to go to 0, and then you'd have that constant times 0, so you would still get 0. So I would expand that property to say it doesn't have to just be 1 over x to the r. If you have any number over x to the r, that limit, as you approach positive or negative infinity, is going to be 0. So example 3, they ask us to find the limit as x approaches infinity of this rational function. And we've seen before that when we try to find limits, if they're not well behaved or they're not immediately obvious, we can pull anything out of our algebraic toolbox that might be helpful. And so they suggest to me for this that I divide everything in the numerator and the denominator by the highest power of x in the denominator. I know that seems really random, but you'll see why that's the case in just a second. So if we divide everything by the highest power of x in the denominator, 3x squared divided by x squared would give me 3. Negative x divided by x squared would be negative 1 over x, negative 2 over x squared. And then down here, 5x squared divided by x squared, 4x over x squared, 1 over x squared. Now, if I go through and I take those limits, the limit of any constant is that constant, so the limit of 3 is 3. The limit of a number divided by a variable when we're approaching infinity, we just had that property that told me that would be 0. Limit of a number over a variable, 0. In my denominator, limit of a constant is a constant. Number over a variable, number over a variable. So by dividing everything by the highest power of x in the denominator, I create nothing but constants and numbers divided by variables that I can use that property that we just learned. And if I can find the infinite limits, that also gives me another way that I can find my horizontal asymptotes, right? And if we go back to that thing at the very beginning we talked about Precalc, where we had said you could compare the degree of the numerator and denominator. When the degree of the numerator and the degree of the denominator are the same, we use leading coefficient over leading coefficient to get the horizontal asymptote. If I know that an infinite limit and a horizontal asymptote are limit at infinity and a horizontal asymptote are the same thing, then I can use those rules for horizontal asymptotes to help me find these limits as well.